which is that we have.
Could you wait just a second, please?
Okay.
Yeah. Thank you.
We have some graph, directed graph with n vertices and m edges. For example, like this, and what we want to do is add some edges, possibly 0 of them, such that the resulting graph will be a single strongly connected component. In other words, that for each of those vertices, it's possible the directed edges and reach any other vertex. It isn't enough to just find the number of edges, unlike in other problems where it was always just find some maximum number and never how to obtain it. In this case, you also need to find what edges to add in order to reach this configuration. First of all, let's handle the case where we could have some completely disconnected components, such that even if the edges weren't directed, then it wouldn't be possible to reach some vertex from some other vertex. Well, if we handle each connected component independently, turn it into a strongly connected component, and then just add in whatever way, just pick some vertex from one of those components, one vertex from the other component, and add 2 edges like this. It will be always enough to reach, if it's possible to reach any vertex in one component from any other vertex in that component, then it's also always possible to reach any vertex in one component from any vertex in any other component. This is simple, so it's just so it's just the number of disconnected components times 2. A case with a single connected component, which doesn't have to be strongly connected. So the graph I drew here is a directed acyclic graph. There is no cycle in it. We could add, I don't know, for example, an edge like this, which would make this a cycle, so any vertex on this cycle is reachable from any other vertex in this cycle. And in general, instead of cycles, we can take strongly connected components in the original graph. So, for example, in this graph, this would be a strongly connected component. This, and this would be independent strongly connected components containing just one vertex each. There is a standard algorithm which is used for finding connected components. It's based on DFS, and it basically goes like this. We mark at first all vertices as unvisited, and then start at this. At whichever vertex is unvisited so far, and do a DFS. To each vertex, whenever we visit it, we give an ID which corresponds to the order in which we visited those vertices. So if we visit this vertex as the first, this vertex as the second, this vertex as the third, in a DFS, then we will look here and see that this vertex is already visited, so we don't visit it again. But we would go back, and then visit this vertex as the fourth, and then from this vertex again using DFS visit this one as the fifth. There is no way to visit this vertex using this DFS, so we just go back. This is already visited, so we don't do anything and stop. And then we would do the same on this vertex, which is the last one left unvisited. And what we do using during one such iteration of the DFS is that for each vertex we remember the ID of the smallest ID of a vertex which can be visited when going back from it, using edges which weren't used to get to new vertices in the DFS. So in this case it would be all those edges I haven't marked in bold. These backwards edges are just direct edges. In this case we just want the backwards edges and always what happens is that when we are at some vertex, try to go along some edge, but see that there already is a path from the vertex which is at the end of this edge to this vertex. So if we keep a DFS stack, which is a sequence of vertices that we have visited so far before this vertex, then we just remember whether this vertex is at the stack. And if it is at the stack, then the minimum ID of the vertex which is visitable from, which is reachable from this vertex would be taken to be min of 3 and 1, the ID of this. And when we go back from some vertex, then we also check what was the minimum ID that was reachable from the vertex from which we went back. And for this vertex we would take, so this is min ID equal to 1 for this vertex. For this vertex it would also be min ID equal to 1 etc. And when we reach some vertex, for this vertex, for example, it would be min ID equal to 4, and we would go back here. This vertex isn't a back vertex. This edge isn't a back edge, so we wouldn't use it. We would, and anyway, this min ID is greater. But yeah, it's that when you look at this edge, this min ID is anyway greater than 1, so we just don't care about it. In this case, we take when we went back from this vertex to here, then we take min ID from this vertex and take min ID for this vertex to be minimum of this and its index, or its min ID, which is in this case again min ID equal to 1 for this. And what we get here is that its min ID is obviously equal to 1 because also its ID is equal to 1. Note that these IDs are completely different from the IDs that were assigned to the vertices on the input, but it just doesn't really matter. You just have to keep the distinction. And when we see that ID and min ID are identical, then this vertex has to be in the root in the DFS of its connected component. Of course, since we are doing a DFS, then whenever we get to some connected, whenever we reach some connected, strongly connected component using the DFS, then all the vertices we reach from it will always be either in this connected component or some connected components that are reachable from that. But since whenever we see that ID and min ID are the same, then we take all those vertices that were previously processed, that were on the stack, and take them all away up to this vertex. We also take this vertex away from that stack, from that list of vertices that were previously processed, and that means that all vertices that were in strongly connected components that were reachable from. So this was already discarded from that list, from the stack. This was also already discarded. For each vertex, we just remember whether it is in that stack. So we are left with these three vertices when we are going back from this. And we can see that these are in one connected component. And at the end, as we did this, we found, every time we found this, we just popped all vertices that were still on the stack up to this one from the stack, and this formed one connected component. So we know which vertices are in which strongly connected component. This algorithm runs in O(n plus m). Clearly, since it's just DFS with some bonuses. What's it called? Tarian's algorithm? Or yes, Tarian's strongly connected components algorithm. You can find it in Wikipedia or wherever. The implementation is quite simple using this. There is a pseudocode based on which you can implement it. This isn't even something you don't need to remember, but can just copy because it's sufficiently simple to write. It's just DFS. We run this algorithm and find strongly connected components. Then we can merge all vertices in each connected component to one, and just instead of thinking about which vertices from that component to add edges from or to, we can just pick one vertex and say that whenever we add an edge from this connected component, it will be in the resulting solution in what we print, it will be an edge from vertex 1, which is the root or the first vertex we found in this connected component. So now when we take always one vertex instead of one strongly connected component, and take all edges that already exist to start or end in that vertex for that component. So instead of we would take vertex 1 as this placeholder for this connected component. Then we would take vertex 4, 5, and this would be 6, for example. And these edges don't matter, but here we have an edge 1 to 4, and we also have an edge 2 to 4, which would be the same, an edge 1 to 4. If we had, for example, an edge from 5 to 4, so these two would be in the same connected component. Then if we would have an edge from 3 to 5, then there would just be an edge from 6 to 4, which would be from this connected component to this connected component. And instead of this edge 3 to 5, we would again have an edge 1 to 4, which is from this connected component to this. The graph we are left with is a directed acyclic graph. So there are each connected contains only one vertex, always that one we chose from that original connected component. And we can see that in this graph, if we have we have three types of vertices. we have sources, which are vertices which have only edges going out of them, so in degree 0. Then we have sinks, which are vertices with out degree 0, so only edges going into them. And then there are some middle vertices. We don't need to care about the middle vertices, because if we know that it's possible to reach from this vertex to this, then it's possible to reach from this vertex to this too, and so on. So always when we can reach from any vertex here, then we can reach from any vertex here, and if we can reach from any vertex, if we can reach from here to any vertex, then we can reach from here to any vertex too, because we go through this. So we don't need to care about these vertices. And the only thing that matters are the sources and the sinks. So we can draw sources and sinks independently and make a bipartite graph out of them. It's possible to have a connected component that contains only one vertex and has 0 in degree and 0 out degree, which is uninteresting. We don't need to do anything for it. We just add 2 edges, connecting it to some other connecting to some other component, and so the only interesting case is when each source has out degree at least 1 and each sink has in degree at least 1. And okay, the new part, the part that isn't completely standard, starts here, because what we need to do is find a path from, for example, the first sink, from the first source to any sink. I'll just draw it as a straight path. And let's say that we had some other sinks. And some other sources. And okay, we just pick one source and look for paths to sinks. If we find a sink which hasn't been matched with any source before, then we mark that sink as matched with this source and continue to the next. It's possible that we've found a source such that it's only matched to already matched sinks, in which case, well, I'll mark the matching paths in bold. It's possible to have this case where we have a source and there are only paths from it to already matched sinks, and it's possible to have sinks such that there are already paths from those things only to those things only from already matched sources. But it's not possible to find a path which is from an unmatched source to some unmatched sink, because if this happened, then we could then we would have found that path from if we did the search for the unmatched sinks so far from this source. So what we found here is a maximal matching. In the previous problem we had maximum matching, and in this problem we have a maximal matching. There is a distinction between these two terms, that if it's a maximal matching, then we can't just pick a path or an edge which will give us a directly larger matching, but we have to remove some flow to get a larger matching possibly. And a maximum matching is the one where it's already maximum. There is no way to remove something and add something new that would give us a larger matching. So this is and in the previous problem we had maximum the maximal matching can be a lot smaller than the maximum, but it just has that property that there is no edge, or in our case, no path from an unmatched vertex on one side to an unmatched vertex on the other side. So, maximal matching, and when we have this, it's straightforward. It's rather straightforward to put all those vertices on one directed cycle, since when we put them on one directed cycle, then they will definitely be in one strongly connected component. So we start with this vertex, go to this vertex, and add an edge to here. Go to this, then go to this vertex and add an edge to here, then go to this vertex. And here we have to distinguish between the case when we have more sinks than sources and when we have more sources than sinks. It's basically symmetric, but I'll just assume that we have more sinks than sources. In this case, here we have one. These two will be separate, but from here we went here, and now we'll go here, add one edge here. Then we'll add one edge here. And then, okay, so all those matched pairs are already on one directed cycle, and all those excess sources, so number of sources minus number of sinks is the number of sources, is the number of sinks minus number of sources is the number of we already put on the directed cycle. What's left are those pairs of unmatched sources and unmatched sinks. But we have this cycle, this directed cycle, and we know that there is an edge or a path from this cycle to any of the sources. And from this source we can add to a corresponding, from this sink we can add one edge to a corresponding source. And from this source, we already know that there is a path back to some matched sink, which is on the directed cycle. So we had this cycle, and we added an edge like this, so that we would connect this whole thing to the directed cycle. It's possible for us to have some more leftover sources and sinks, in which case we again just add edges like this, and again there will be a connection of this thing with the directed cycle. So in the end everything will lie in the cycle. How many edges did we use? Well, for each of these leftover sinks, we used one edge back to a leftover corresponding source. Then for each of the matched sinks, we used either one edge to the next matched source, or from the last one of them, we used one edge to one of those remaining sinks, and then we connected all those remaining sinks, and from the last of those remaining sinks we used one edge and put it back to the first source in this bipartite graph. And therefore we can see that from each sink we made one new edge. So the total number of edges in the case when there are more sinks than sources is equal to the number of sinks. If there are more sources than sinks, then we need at least one edge from any source, and if there are more sinks, then we need at least one edge from any sink. So the number of edges we used here is minimum. number of edges added is equal to the minimum of number of source strongly connected components and the number of sink strongly connected components. This hash sign is often used to denote a number of something.
Isn't it maximum? The maximum
Right, max. Which can be guessed, but there is this construction which is quite hard to figure out. So that's why this problem was the hardest. Nobody solved it actually in the original City Open contest, which was last year. And okay, we are left with the last problem, which is actually simple, but I saved it for last because I can tie it to some other problems. So this problem we had is that we have a permutation of numbers, or well, we can start with an array of distinct numbers, but then put all those numbers in a map, which would let us compress them and take them to be a permutation of numbers 1 to n, p1, p2 through pn. And we want to sort these numbers to make, instead of this arbitrary permutation, just numbers 1, 2, 3, etc. up to n. In one step, we can take two numbers and swap them. For example, like this, and this is a very well-known problem where the number of swaps we need to make is equal to the number of pi, such that pi is not equal to I minus the number of cycles in that permutation. It's obvious that it has to be that each number has to be moved at least once. It's not obvious why is this minus number of cycles, but the proof uses one useful property of swaps in permutations, that if we have some, for example, a permutation like this, 1, 2, 4, 5, 6. Okay, a permutation of 6 numbers, and then we can make from each permutation a graph which is composed of cycles. These are the cycles I'm talking about here, and from each vertex in this graph we will have one edge from vertex I, we will have one edge to vertex pi. So this is a graph of a permutation P. And what happens when we swap some two numbers, for example 2 and 5, here is that if they are on the same cycle, then then this cycle is split into two, and if they are on different cycles, then these cycles are merged. So if we split this cycle by swapping P2 and P5, so P2 in this case is 6. Then we will have P5 is 1. So if we swap the numbers P2 and P5, then we would instead of having 6 and 1, we would have 1 and 6. So this edge from 2 to 6 is removed. The edge from 5 to 1 is removed. We make an edge from 5 to 6 and make an edge from 1 to 2. You can see that this splits the cycle. So again, if we make a swap between two elements of the permutation, two vertices that are on the same cycle, then this cycle is split into two cycles. And if we make a swap between two elements of the permutation or two vertices that are on different cycles, then we merge those cycles. And from this, it's clear that since the final permutation that one we want is 1 to up to n, where pi equals I, so each vertex has just an edge to itself. So it has n cycles. And the number of so there are cycles in total in them, in that permutation. And in one step we can split at most one cycle into two, so the number of cycles in the resulting permutation is always increased only by 1 in one step. So the minimum number of steps we need is n minus the number of cycles in the initial permutation in total. Here the number of cycles which I wrote is just from these elements. So we discard elements where pi doesn't equal I. And from that we can see that this formula and this formula are actually the same, since here we just discarded elements which are on cycles of length 1, which only have edges to themselves, which are elements where pi equals I. What we wanted to find is in this problem isn't a way to split all those the permutation and to order it into 1 through n, but just the number of operations which we need to make. So we can either count the cycles with length at least 2 and count the elements which are different from their pi, and then compute this formula, or we can just count the number of cycles in total, including those simple cycles of length 1, where there is just one edge to its own vertex, and subtract it from n. And this is also, if we wanted to find a construction of this, we could just in the original, we could just swap always two elements which are adjacent on a cycle. If we swap, for example, P5 and P6, then it will give us a permutation like this. So this element will become its own cycle, and we would have a cycle with size 1 less. So it's also quite easy to find the construction here. These are all the problems from this contest. Also, this is obviously an ON algorithm. these are all the problems from this contest, but this last problem has some interesting variations on it.
Actually, there is one more, right?
Which one?
Problem B.
Oh, right, that roller coaster. Okay, I'll go back to this. I'll just describe this interesting problem. There's a variation on this. So instead of having cost 1 for swapping two numbers, we could have cost, for example, for swapping P2 and P5, the cost would be P2 plus P5 instead of 1. And we want to sort the permutation in the minimum cost. Not just the minimum number of operations, but the minimum cost. This, again, the solution uses the fact that if we split if we swap two numbers in one cycle, then the cycle splits, and that we can often just take one vertex from this cycle and swap it with a vertex from another cycle, and swap it with the next vertex on that cycle. But I'll let you think about the solution because it's an interesting problem, and we probably can have. You probably won't have so much time now when I finish. So the last problem which I haven't described is that we have some points again in a two-dimensional plane or on an integer grid. So the points have integer coordinates, and we want to find out something that's related to maximum, either counting the number of squares or counting the number of rectangles, or finding the maximum square or finding the maximum rectangle. Is not very important what we want to find, because the techniques for all those things I mentioned are basically the same. Maximum possible distance between 2 points. It was. Yeah. And the point is that we split. We take all vertical lines on which some points appear. And we split them into two types. There are vertical lines that contain up to square root of n points, and vertical lines that contain over square root of n points. The advantage of these lines is that the number of which are on such a line, on each such line is at most equal to number of points squared, which is at most number of times sqrtn. And in here, the number of pairs of points could maybe possibly be large, but the number of such lines is at most sqrtn, the square root of n. That's because if each of these lines has over square root of n points, so if there were more lines, then there will be at least number of lines times sqrtn points, and that would be over n, and we only have n points. Okay, so we want to find all rectangles that are in those selected grid points, that all 4 vertices of such a rectangle are in those n grid points. So either we have this either we have some rectangle. The optimal rectangle is either containing 2 points that lie on one of those lines, and possibly the other line could have more points. But in this case, the number of possible pairs that are here of the rectangle is one of those lines with over sqrt endpoints, then we can try all possible choices for one line, all possible choices for the other line, and then do some algorithm in linear time over this, or n log n time, or linear times log time over the number of points in total on these two lines. So for each of these lines and each of the points on these lines, we only look at this point as many times as there are these lines, because for one of the points on the lines containing many points, we only look at it for each of these remaining lines containing many points. So. And then there are the cases where
it this vertex to that.
Yeah.
And if you pick this vertex, you are assigned this vertex to this vertex. And this graph is not strongly coupled.
No, that's why you need to add some edges. And since in this case you would have just it's that you assign this to this, you assign this to this.
Yes.
So you add an edge.
Yes.
And add an edge. So these aren't edges, so we'll delete them. And this graph already is strongly connected.
Great. Yes. Perfect. Thanks.
No problem. So anyway, I don't remember how this case where one pair is is on a line with a small number of points and one pair on a line with large number of points is solved. So sorry, just think about it for yourselves how to solve this with this trick with splitting lines into ones with up to squared endpoints and over SQRT endpoints. And there was some other approach that was quite similar, where we just for each point here we take we look at how many points are on this line, how many points are this line, and try to pair it up with the either vertical or horizontal line on which there are on which there is the smaller number of points, and then finish by adding the two by checking if there is by triangle remaining points and checking if there is the fourth point. But that had some solutions with map and with extra algorithms. In this problem the data were kind of weak, and probably some O n squared could have passed, and O n square root of n log n could also easily pass. This is basically what the organizers expected to pass, which might explain why this why these quadratic solutions passed so easily. And yeah, there was one thing I wanted to mention. If there was some time left, and it seems if I will try to solve this just now, then there is some time left, and that's how to compute a series of this form 1 plus x to the power of n, where x can be something more complicated. For example, what if this x is a matrix, not an integer, because for or a real number, because for real numbers it's easy to compute it as the sum of geometric series 1 minus x to the power of n plus 1 divided by 1 minus x, or 1 times n plus 1 if if x equals 1. But if, for example, x is a matrix, then okay, this case is again simple. It's the unit matrix times n plus 1. But if we had to compute this and its inverse, because there are some matrices which can be inverted. multiplication, that fast exponentiation, and some, again, splitting into two of this formula. So if we have n, if n is even, well, let's denote this by Sn, then Sn can be computed as Sn minus 1 plus x to the power of n, because n minus 1 is just all terms except this last one, and then we find the nth power of x, or alternatively we can compute it like this, with where this would be found using fast exponentiation, but this is just multiplication, so it's kind of simpler. And if n is odd, then the number of terms in this formula is even, because it's the exponent goes from 0 to n, so from an even number to an odd number. And in this case we would split the formula to 1 plus Sn equals 1 plus x to the power of n half minus 1, or I can write it as n minus 1 divided by 2. So these are in total n plus 1 divided by 2 elements out of this n plus 1 here, and then plus x to the power of n plus 1 half plus up to x to the power of n. Okay, this is just the sum for s n minus 1 divided by 2, and this again is just the formula for n minus 1 divided by 2, because it's the sum of x to the power of 0.
Where is x power n divided by 2?
This?
No, n divided by 2. Where is
N divided by 2?
yeah.
N divided by 2 doesn't exist for n odd. I'm just writing it. Yes, the number of terms in this sum is n plus 1, because it goes from x to the power of 0. So when n is even, then we just do this, and when n is odd, the number of terms is even. N minus 1 is even, and n plus 1 is even, so we can divide it by 2 and not worry about some integer division. So anyway, this is actually the same formula as this, just with every element multiplied by x to the power of n plus 1 divided by 2, because this is x to the power of 0 times x to the power of n plus 1 half. Then there is x to the power of 1 times x to the power of n plus 1 half etc. up to x to the power of n minus 1 half times x to the power of n plus 1 half, which is x to the power of n, because n minus 1 half plus n plus 1 half is 2n divided by 2, which is n. So this is the same formula as we have in this bracket, just multiplied by x to the power of n plus 1 half. So if I write this formula and this formula, use it to get this is equal to Sn, so we can just compute this smaller Sn minus 1/2, and this this is the same Sn minus 1/2, so this is recursively computed Sn minus 1/2 times. Well, we have to compute this using fast exponentiation, add 1 or whatever is 1 in that a system in which we have x. For example, for matrices, the identity matrix, and then multiply it by that recursively computed sum. So the time complexity of this would be O log squared n times 1. The number of steps we do like this, in each step we get from n to something like n.5, so the number of steps is recursive steps is approximately the logarithm of n, and in each of these steps each two of these steps we always have to compute 1 power of x, which is again in some logarithm of n. And then there is this time of multiplication, because we can have something like matrices with large size. Multiplication doesn't have to be doesn't have to be just a constant like for integers. For matrices with size square matrices, some m times m, the multiplication would take m to the power of 3. There are of course some faster algorithms that work in m to the power of some 2.2, 2.4, something like that. But the constant they have is so bad that it's not worth using them, not even for copy pasting, unless we have some totally massive matrices. Okay, it's 12:30, so you can think about how to finish this problem. You can think about how to finish this problem. This modified sorting of the permutational array of distinct integers, and unfortunately I found out that there are no public test data or downloadable test data for today's contest, so you won't do it on Codeforces, but I'll just give you a link and you can just directly solve problems at that link. Okay, thank you for your attention. Let's see you at the contest.